Right, how do I pop out chat again? I will never remember how to do any of this, to be entirely honest. Not gonna happen. Yeah, there we go. Hey, looks good. Probably. Who knows? Right, where exactly are we? Where is... Ah, here we are, probably. But let's just get rid of all this junk. Apologies, this really isn't where I normally use my stuff. Use the stuff? Apologies. This isn't my normal browser. I use Florp for some reason. I like it. Okay, now I'm just gonna wait for a few people to pop in if they do. If at 7:40-ish nobody's here, I'm just gonna continue going on. Alright, perhaps I should put something out there. I don't actually know. Is audio even coming to Twitch is the question. Looks like it. How about YouTube? Right. Any of you use Piped? The nobody who exists in this channel's nobody's watching right now. I doubt anyone's gonna watch for this one. Yeah, I didn't put out much in the way of what is it called? Notice. But who cares? Right, are we currently streaming? What's going on? I have no idea how to tell. I hate YouTube. Twitch is just so much easier to use. Like, absurdly easier to use. Like, you'd think this massive corporation that has been using video for decades would have a bit of a better UI than this, but no. Yeah, I'm not even allowed to watch it from here. I have to go through like 30 hoops. That's fantastic. Thank you. Studio. Let's try just... Right. My channel. Here we go. Y'all can't see any of this, which is fun. Here we go. Do we have anything on? Okay. Looks like we have audio. Just going to check one thing. I'm playing copyrighted music, but I hope that it's not going off the stream. That would kind of suck. A little bit suck. No, looks like it's not. Fantastic. Okay, I guess I fixed it. It was the audio source in OBS. I have no idea what any of this does. Wow, that puts an infinite hall effect. I mean, somebody's into that, you know? Quite cool. Right, literally no one's coming, which is okay. I'll just go through it. The VOD will be up, but bit of a shame. I like the conversation piece to this. I may just make the post. Where would that be? That would be here. Right, let's do this live. I don't know what I'm doing, to be entirely honest. slow as hell. I'm just going to copy Magel's entire post, and I'm just going to place it into a new post, which will work, probably. I'll edit it as we go on. Create a post. Body. Let's clear my history. This is apparently for week 2. I don't understand what he did here. We have the reading, Twitch stream, video tutorials. For the section, learning basics makes a great piece on Peer2. Okay, looks like on Peer2 we have number 2. We're probably going to want number 3. Now, I had some guy contact me about maybe doing a stream in Europe, which is fantastic. So we'll have that up eventually for the people who want to be following along like that. But he had been asking about putting it onto PeerTube. Now, I don't know much about how PeerTube works. I don't think I can create an account on Diode Zone. I looked into it, not a clue how to. I don't think I can because they're not open, which is okay, but a bit disappointing, you know? Maybe able to find one which I can upload all of this series to. I like the idea of PeerTube and would love to no longer stream to YouTube. Be great. Right, here we go. Is this the correct thing? Yep. Right, I'm just gonna have to ask Magel how to do... Yeah, I don't know how to do that, so I'm just not going to worry about it. What's next week? Chapter 5. Right, Chapter 5 will be... Where am I going? Chapter 5 is going to be using structs to structure related data. I really don't like the way he's organized this, to be honest, but I'm not going to change it right now. This will be done. Apologies, just to confirm what I'm doing here, I am simply editing or sending out a post, hopefully get some people in here. I understand that there isn't. Is it Tuesday? It is in fact Tuesday, good. Reading. Chapter 3. I'm just editing this stuff out. I assume this is going to get to the correct placement. I'm going to have to go back through this. Alright, basic fun. I'm not going to... I'll write all the rest of this later. This is really just supposed to act as a bit of an announcement post, I guess. Week 3, project. As you can tell, I'm not exactly good in this community management thing. Magel just gave me the admin privileges so I can pin posts, really. Not gonna overstep anything past that. That's the Twitch stream. That is, well, that's what you're looking at right now. If you're looking at this. Well, no, you're not looking at this, meaning that will be the YouTube channel. Yep. Oh, 3. Memory and ownership seems to be going over the same thing we're going over. Fantastic. This is just talking about what's next week. Let's preview this. See if I messed stuff up royally. Looks like I did. No idea what that is. That shouldn't be. That's not how this is. Why is it like that? This is supposed to be just. That should. I don't know. I have no idea why. Lemming Markdown is a bit trash. Can I just try and get it to bullet point? Bullet point. Yeah, it's supposed to just be minusing, correct. Well, this is riveting content that I should probably cut out if I can figure that out. I have not figured out how to figure that out. That's not going to work. Right. Let's just look at raw. That's what I should have done. What in the world is that? Right, so the stars? Stars for this. Well, that's fantastic. Don't we just love Markdown? I definitely should have done this before starting stream, but I had a lot of things to deal with. Apologies about the lack of responsiveness recently. I am honestly surprised that I could get here today. Still, the greatest. This was a massive blunder. Why is it a star instead of a dash like every other thing, you know? I'm sure they have their reason. Somebody with a bit of web development experience should probably go and try and fix some of this stuff. Clarify, I am literally web dev. That's my job. I should go in and fix this stuff. Okay. I can probably cut all this out of YouTube, but I don't know. I saw some editing tools. I'll look into that later. But I'm just going to assume that's fine for right now and start reading ownership, understanding ownership. At the very least, it'll be a way for me to, oh hey, we have one more guy who jumped in. Right, to explain what I just did, I just sent out a request for people to join in on Lemmy. If you're not from Lemmy, great place, look into it. Love to see you there. What we're going to do right now is go through Chapter 4, Understanding Ownership. Previously, we had gone through common programming concepts, variables, immutability, data size, function, comments, control flows, some very interesting stuff, specifically around scoping, which I quite like. Hey, not a problem. I just, I was a bit late myself. Also had some issues getting, I just wanted to write a post about this, get some people in perhaps. But I'm very glad to see you in here. Good to see somebody that I can talk to during the thing. Thank you for being here, Keith. By the way, we are getting a new guy going to host. Can't remember his name right now, but he's going to be coming in from Europe. Going to be doing a secondary one for people who are in that time zone. Right. I am very glad to see you, though, Keith. First, I'm going to cd into Rust for Linux, make my directory, the into it. Oh, hey, Silver Sorbet! Welcome in. Not a worry. Hey, that's the two of you. Great to have some conversation. I was kind of worried nobody would be here because I did not put anything out. I was just talking about that, not a single thing about what was going on today. Entirely my bad. Missing size. Thank you, T-Mux. You are great. Okay, so I guess we can really just start out. I have no issue with that. We took some time to start here. My bad. But I'm just going to start reading this out. Understanding ownership. Ownership is Rust's most unique feature and has a deep... Ownership is Rust's most unique feature and has deep implications for the rest of the language. It enables Rust to make memory safety guarantees without needing a garbage collector. So it's important to understand how ownership works. In this chapter, we talk about ownership as well as several related features. Borrowing, slices, how Rust lays data out in memory. Very happy to see. What is ownership? Ownership is a discipline for ensuring the safety of Rust programs. To understand ownership, we first need to understand what makes a Rust program safe, or unsafe. Safety is the absence of undefined behavior. Let's start with an example. This program is safe to execute. We have a simple function, we have an if statement. If y, which is a boolean, is true, we print y is true. Else, we simply end. Then main, simply, let's x equal true, read x. Fantastic. We can make this program unsafe to execute by moving the call to read before the definition of x. Oh no, x isn't defined. Yep. We are trying to read a value that is not there. Right, so Rust will check at compile time whether or not everything is instantiated before it is read. In this chapter, we'll use many code examples that do not compile. Make sure to look. The question mark crab, I didn't notice this little guy. I'll admit, I am not looking very hard. I like him, little friend. Make sure to look for the mark crab. I don't know how this works in C, actually. I mean, we could try. Can't really remember too much. To define default value? I'm sorry, I don't understand what you mean. But if we tried this, it would just fail out. X is uninstantiated, so in C, I'm fairly certain this wouldn't print out anything. This would just crash at runtime. But what do you mean by define a default value? Some classes I was told it was good practice to always give things value, not let the garbage that is in mem be the value. Yeah, I guess so. I guess in Rust, it's... I doubt it's bad practice, but I guess we'll see. Apologies for that. Yeah, good point. Of course, if there's some unsafe practice going on from another application, it can alter your memory anyway, but that's not really your fault. Yeah, I guess we'll really see what best practice is with instantiating a variable. The second program is unsafe because read x expects x to have a type of bool, but x doesn't have a value yet. When a program like this is executed by an interpreter, and reading X before it's defined would raise an exception, such as Python's named error, JavaScript's reference error. But exceptions come at a cost. Each time an interpreted program reads a variable, and the interpreter must check whether that variable is defined, making compile times very long in Rust. So if there's a runtime error, you would be able to trace it up. Sorry, you had already said that. Rust's goal is to compile programs into efficient binaries that require as few runtime checks as possible. Therefore, Rust does not check at runtime whether a variable is defined before being used. Instead, checks at compile time. If you would try to compile an unsafe program, you get this error. Cannot find value X in the scope. From this position, oh no, X isn't defined. Oh, that's a comment. Not found in this scope. X. Oh, I like that error, that it's specifically not found in this scope. Not X doesn't exist. I think that makes it a bit lighter on the person being like, hey, X should exist here, if he believes it should, but of course not in this scope. It's funny that it does it here. Oh, no, it's not funny that it does it here, you idiot. Of course it doesn't do it there. Or sorry, of course it does it there. What am I talking about? Right. You probably have the intuition that it's good for us to expect the variables are defined before they are used. But why? To justify the rule, we have to ask, what would happen if Rust allowed a rejected program to compile? I guess here's where we get the answer to your question. Let's first consider how the safe program compiles and executes. On a computer with a processor using the x86 architecture, Rust generates the following assembly code for the main function in a safe program. With the label of main, we have comment, I believe. I don't know what this... Oh, that's just an ellipsis saying there's more stuff. Move, EDI, 1, call, read. Not a clue what that means. If you aren't familiar with the assembly code, that's okay. This section contains a few examples of assembly that just to show you how Rust actually works under the hood. You don't generally need to know assembly to understand Rust. This assembly code will move the number 1, representing true, to a register kind of assembly variable called EDI. Call the read function, which expects its first argument y to be in the EDI registry. The unsafe function was allowed to compile. Its assembly might look like call read mov EDI :1. Mov is after call. This program is unsafe because read will expect EDI to be a boolean, which is either the number 0 or 1, but EDI can be... yeah, you're entirely right. Apologies for that. It could just be whatever junk is in the memory. Sorry about that, Keith. When read wants to use this argument y for any purpose, it will immediately cause undefined behavior. Rust doesn't specify what happens if you try and run if y when y isn't true or false. Behavior, or what happens after executing that instruction, is undefined. Something will happen. For example, code executes without crashing, no one notices a problem. Code immediately crashes due to a segmentation fault, or another kind of operating system error. The code executes without crashing until a malicious actor creates the right input to delete your production database, overwrite your backups, and steal your lunch money. You know what, he deserves it, honestly. A fundamental goal of Rust is to ensure that your programs never have undefined behavior. That is the meaning of safety. Undefined behavior is especially dangerous for low-level programs with direct access to memory. About 70% of reported security vulnerabilities in low-level systems are caused by memory corruption, which is one form of memory behavior. Now, this is that Microsoft blog everybody see. Good read. Don't remember a word of what it said. A secondary goal of Rust is to prevent undefined behavior at compile time instead of runtime. This goal has two motivations. Catching bug at compile time means avoiding those bugs in production, improving the readability of your software. Catching bugs at compile time means fewer runtime checks for those bugs, improving the performance of your software at the price of compile time. Rust cannot prevent all bugs. If an application exposes a public and unauthenticated delete production database endpoint, then a malicious actor doesn't need a suspicious if statement to delete the database. But Rust protections are still likely to make programs safer versus using a language with fewer protections. For example, as found by Google's Android team. In this link, we're just going to get a bunch of articles praising Rust. I'm not going to read them. Apologies. Ownership as a discipline for memory safety. Since safety is the absence of undefined behavior, and since ownership is about safety, then we need to understand ownership in terms of the undefined behavior it represents. I am too. All praise God Crab King. Hey, Crab King's already a thing. Hell yeah, but the crab cycle repeats. For now, we will focus on one category: operations on memory. Memory is a space where data is stored during the execution of a program. There are many ways to think about memory. If you are unfamiliar with systems programming, you may think of memory at a high level, like memory is the RAM in my computer, or memory is the thing that runs out if I load too much data. If you are familiar with systems programming, you might think of memory at the low level, like memory is an array of bytes, or memory is the pointers I get back from malloc. I always visualize it as a massive cubbyhole system with whiteboards in them. Both of these memory models are valid. They are not useful ways to think about how Rust works. The high-level model is too abstract to explain how Rust works. You need to understand the concept of a pointer. For instance, the low-level model is too concrete to explain how Rust works. Rust does not allow you to interpret memory as an array of bytes, for instance. Really? Rust provides a particular way to think about memory. Ownership is a discipline for safely using memory within that way of thinking. The rest of this chapter will explain the Rust model of memory. Variables live in the stack. Here's a program, like the one you saw in section 3.3, that defines a number, n. Calls a function +1 or n. +1 on n. Beneath that program is a new kind of diagram. The diagram visualizes the contents of memory during the program's execution at the 3 marked points. Let n equal 5. Y equal +1 n. +1 is a function expecting an I32 called x, which is x plus 1. So y would equal 6. Print line. Value of y is y. Oh, I see, yeah. Right, so the stack, we have n, which is 5. We have stack, main, and +1, two different methods having ownership over these. Oh, so +1 owns this x, I guess? Okay. And then the stack has main owning n is 5 and y is 6. Variables live in frames. A frame is a mapping from variables to values within a single scope, such as a function. For example, the frame for main at location L1 holds n equals 5. Frame for +1 at L2 holds x equals 5. Frame for main at location 3 holds n equals 5, y equals 6. Both are held within the main frame. I hate that. Okay. Frames are organized into a stack of currently called functions. For example, at L2, frame for main sits above the frame for the called function +1. After a function returns, Rust deallocates the function's frame. The allocation is also called freeing or dropping. We use those terms interchangeably. This sequence of frames is called a stack because the most recent frame added is always the next frame freed. Okay. Look, that's how it can all live on the same stack, I guess, yeah? or the stack. This memory model does not fully describe how Rust actually works. As we saw earlier with the assembly code, the Rust compiler might put n or x into a registry rather than a stack frame. That distinction is an implementation detail. It shouldn't change your understanding of safety in Rust, so we can focus on the simpler case of frame-only variables. In an expression, when an expression reads a variable, the variable's value is copied from a slot in the stack frame. For example, if we run this program, let a equal 5, let a mute b equals a, b plus equals 1. At location 1, a equals 5, location 2, a and b equal 5. Yep, and yeah, I guess that's all stating here is that instead of being a reference, b equals exactly a, it's just copying the value over as you would expect. The value of a is copied into b, and a is left unchanged, even after changing b. Boxes live in the heap. However, copying data can take up a lot of memory. For example, here's a slightly different program. This program copies an array with 1 million elements. Okay, yeah. We have A, which is just an array of 1 million elements, all initialized to 0. Then we're having B, which is equal to A, copying 1 million elements into B. Observe that copying A into B causes the mainframe to contain 2 million elements. To transfer access to data without copying it, Rust uses pointers. A pointer is a value that describes a location in memory. The value that a pointer points to is called its point E. One common way to make a pointer is to allocate memory in the heap. The heap is a separate region of memory where data can live indefinitely. Heap data is not tied to a specific stack frame. Rust provides a construct called box for putting this data on the heap. For example, you can wrap the million element array in box : new, like this. So A would be of type, would A be of type box, or would A be of type, or I guess A would be a pointer? I don't really know. But B equal A, so I guess A would just be a pointer to the box element, or a pointer to the array. Well, the first element in the array, but you know. Observe that now, there is only ever a single array at a time. At location 1, the value of A is a pointer, is represented by dot with an arrow. The array inside the heap. That's a bit of an awkward sentence, but you know. The statement to let b equals a copies a pointer from a into b, but the pointed to data is not copied. Note that a is now grayed out because it has been moved. We will see what that means in a moment. So a can no longer be utilized? Can we no longer utilize a? I really want to check that out. Can we use a? Are we allowed to? We should be able to. Like, why not? I guess that's ownership. Ownership has been transferred from A to B. Just copy this code over. Apologies for taking a moment here. This just seems a bit strange. Exactly. So this is the actual case. So we can't like print. Ah, fuck. How does a print in Rust? I will never remember this. Yeah. Unless I start doing it. So we can confirm. This will give us nothing, correct? Print line. You are correct on that. Thank you. Don't know what print does. Sorry. System.out.println would be Java. Ah, yeah, that's lovely. What? That won't work. How do you... Okay, whatever. I think I understand. Why won't that work? Can we not print out an array like this? Format string expected ending square bracket found, or sorry, curly bracket found bracket. I mean, that won't work because that, well, also is not a string, but whatever. Honestly, I don't care anymore. I'm going to have to assume that A is dead because it has been moved. Where were we exactly? Yeah. A is dead? Right, which of the following best describes the differences between the stack and the heap? The stack holds copyable data, while the heap holds uncopyable data. The stack can hold pointers to data stored on the heap, while the heap only holds data without pointers. The stack holds data associated with a specific function, while the heap holds data that can outlive a function. Correct? The stack holds immutable data, while the heap holds mutable data. Query. Consider the following execution of the code snippet with the final state shown. We have let A is a new box, B equals A, C equals box new 50. Right, so, yep. In the final state, how many copies of the original number 15 live in memory? Write your answer in a digit such as 0 or 1. How many copies of the original number, of the number 15 live anywhere in memory? Okay, so this is poorly worded. This is extremely poorly worded. I mean, I think I understand what they mean. They're asking how many versions of 15 exist, which is 2. A is dead. So this... Well, A isn't... A is no longer a pointer, I guess. A is just completely gone. I guess. Correct? Correct. Rust does not permit manual memory management. Memory management is the process of allocating memory and deallocating memory. In other words, it's the process of finding unused memory and later returning that memory when it is no longer used. Stack frames are automatically managed in Rust. When a function is called, Rust allocates a stack frame for the called function. When the call ends, Rust deallocates the stack frame. As we saw above, heap data is allocated when calling box : new, but when is heap data deallocated? But when is words difficult? Awful time. Imagine that Rust had a free function that frees a heap allocation. Imagine that Rust let a programmer call free whenever they wanted. This kind of manual memory management easily leads to bugs like you forgetting to call free. For example, we could read a pointer to freed memory. Is after free, which is a very bad idea because that'll just post out whatever garbage is within the memory at that point in time. Undefined behavior, pointers used after it's freed. So there's no free in Rust. Good. You may wonder how we are executing this Rust program that doesn't compile. Special tools to simulate Rust. Aquascope. Unsafe Rust? Here we allocate an array on the heap. We call free B, which deallocates the heap memory of B. Therefore, the value of B is a pointer to invalid memory, which we represent as this icon. No undefined behavior has happened yet. The program is still able to live at location 2. It's not necessarily a problem to have an invalid pointer. The undefined behavior happens when we try and use the pointer by reading B square bracket 0 square bracket. This would attempt to access invalid memory, which could cause the program to crash, or worse, it could not crash and return arbitrary data. That is very bad. Rust does not allow programs to manually deallocate memory. That policy avoids the kinds of undefined behavior shown above. A box's owner manages deallocation. Instead, Rust automatically frees a box's heap memory. Here is an almost correct description of Rust's policy for freeing boxes. Box deallocation principle. Almost correct. Why are we having almost correct? Well, I guess just as good as need be. A variable is bound to a box. When Rust deallocates the variable's frame, then Rust deallocates the box's heap memory. Okay? For example, let's trace this program that allocates and frees a box. So we have let a underscore num equal 4, make and drop, which is just, okay, I guess that's just down in memory. Let's a underscore box equal box colon new 5. We have location 1, main a num equals 4. We have that in memory under main. We have main a4, make box and drop is run. We have heap memory 5 within heap memory. A box is a pointer held in the stack, I believe. I guess so. Then once this pointer is dead, so is the heap memory. Okay. Sounds a lot like garbage collection without a garbage collector. I guess that's quite simple. I like that, not having to worry too much. At location 1, before calling make and drop, the state of memory is just the stack frame for main. Then at L2, while calling make and drop, a box points to 5 on the heap. Once make and drop is finished, Rust deallocates its stack frame. Make and drop contains the variable a underscore box, so Rust also deallocates the heap data in a underscore box. Therefore, the heap is empty at location 3. Alright. The box's heap memory has been successfully managed, but what if we abuse this system? Returning to our earlier example, what happens when we bind two variables to a box? The boxed array has now been bound to both A and B. By our almost correct principle, Rust would try to free both the box's heap memory twice on behalf of both variables. That's undefined behavior 2. To avoid this situation, we finally arrive at ownership. When A is bound to box new, the array, we say that A owns the box. The statement B equals A moves ownership of the box from A to B. Given these concepts, Rust's policy for freeing boxes is more accurately described as the allocation principle fully correct. A variable owns a box when Rust deallocates the variable's frame, and Rust deallocates the box's heap memory. Okay, to confirm, so A at this point is dead, it's gone. You can't have multiple pointers to the same thing, I guess, unless you... I suppose there must be some way of doing that. In the example above, B owns the boxed array, therefore, when the scope ends, Rust deallocates the box only once on behalf of B, not A. Boxes are used by Rust data structure, like vect, string, hash map. Boxes are used by Rust data structures like vec, string, and hash map to hold variable numbers of elements. For example, here's a program that creates, moves, and mutates a string. Let first equals string, from, Ferris. Let full equal add underscore suffix first. Add underscore suffix is takes in a mute name, which is a type string and returns a string. Name.push underscore str junior. We have pushed junior to the beginning name, and name is returned. I hate this. I really just wish they would allow us, or not allow us, I guess I really just wish they would put return there. Why in a compiled language are you caring too much about brevity? Like, we're going too far in the other way. You got Java and then you had shell shock, so I hate that. Anyway, from this point, we have print full, which should be junior dot space or space junior dot Ferris. Oh no, that would be push, so that would be Ferris space junior dot. Right, so we have in the stack, we have main first, heap Ferris. Pointer to Ferris within heap. Is yeah. Allocation 2, we have first, which dies. Add underscore suffix is a new function where we have name just brought in, containing Ferris, or sorry, a pointer to Ferris within heap map. Level 3, we have first, still dead, add underscore suffix, name, which is pointer to Ferris Jr. And we have L4, which is just full. Sorry, we have main, where full now contains Ferris Jr. The pointer goes from first, the name is altered, back to full after it is returned. It's going to describe it again. I don't know why I went through that. This program is more involved, so make sure you follow each step. At L1, the string Ferris has been allocated on the heap. It is owned by first. At L2, function add underscore suffix first has been called. This moves ownership of the string from first to name. The string data is not copied, but the pointer to the data is copied. 3. The function name.push underscore string junior resizes the string's heap allocation. This does 3 things. First, it creates a new larger allocation. Second, it writes Ferris space junior into the new allocation. Third, it frees the original heap memory. First now points to deallocated memory. Yeah, okay. Does it? Okay, but it's not going to let you use it, I guess. So yes, first would point to deallocated memory, but we're not allowed to use it. That will have a compile time error. At L4, the frame for add underscore suffix is gone. This function returned name, transferring ownership of the string to full. So what's weird about this is it says first now points to deallocated memory, but first is dead. We're no longer allowed to use it. The ownership has been moved from first to name. Why is free still in memory? I mean, it's stating quite clearly that it is no longer usable, or ownership has been transferred, but still exists in memory? Why? Why does it still exist in memory if it's not usable? Is there a way for us to transfer ownership back? I assume so. Otherwise, well then, in the situation, if ownership was transferred back, then it would have a use after free error. I guess we'll read further. I don't fully understand what's going on there. The string program helps illustrate a key safety principle for ownership. Imagine that first were used in main after calling add underscore suffix. We can simulate such a program and see the undefined behavior that results. That first equals string from Ferris. That full equals add underscore suffix first, which is the same function we've seen before. Print full originally Ferris first. Okay. Pointer used after is pointy is free. Yeah, we're using first. Full originally first. So that would be just random junk, or perhaps it would still be Ferris. It's possible it would still be Ferris, but it's free, meaning the operating system may have already given it to some other program. First points to deallocated memory after calling add underscore suffix. Reading first in print line would therefore be a violation of memory safety undefined behavior. Remember, it's not a problem. First points to deallocated memory. It's a problem that we tried to use first after it became invalid. Okay. I don't understand the subtleties here. What's the difference? So it's okay that it's there, we just aren't allowed to use it. But that does confirm that first does exist in memory, pointing to unallocated memory. Thankfully, Rust will refuse to compile this program, giving the following error. Borrow a moved value first. Let first, move occurs because first has type string, which does not implement the copy trait. Okay. Value moved here. Okay, so it does directly just tell you the reason why it copies, the reason why it moves, and secondarily, the place where the value was moved, and where it is being used. I love Rust's error system. This is really good. That's really helpful if it works like that all the time. Let's walk through the steps of this error. Rust says that first is moved when we call add_suffix first on line 3. The error clarifies that first is moved because it has type string, which does not implement copy. We will discuss copy soon. In brief, you would not get this error if you used an I32 instead of string. Finally, the error says that we use first after being moved. Finally, the error says that we use first after being moved. It's borrowed when we discuss, which we discuss next section. So, if you move a variable, Rust will stop you from using that variable later. More generally, the compiler will enforce this principle. Moved heap data principle. A variable, x, moves ownership of heap data to another variable, y, then x cannot be used after the move. Now you should start to see the relationship between ownership, moves, and safety. Moving ownership of heap data avoids undefined behavior from reading the allocated memory. Cloning avoids moves. One way to avoid moving data is to clone it using the .clone method. For example, we can fix the safety issue in the previous program with a clone. First string clone from first_clone equals first.clone fold equals add suffix first_clone. Do we not just have first_clone here? I mean, why not? It should just return, right? Just gonna quickly see. It should be easy because we just oops, that's not what I wanted to do. Should be quick if I wasn't an idiot. Oops. Would this not work? This should work, right? Yeah, that does work. Okay, it's just for clarity. Good stuff. Just wanted to make sure, if they do something weird like that, who knows if it's for a reason or if they're just doing it for clarity. Alright, so we have first_clone, which have first in it from location 1 to location 2 has first_clone is killed. Well, not killed, it's put into a shed. I don't really know a good analogy for that. You have a thing on it that says, we'll kill your program if you try and use it. Observe that at L1, first_clone does not shallow copy the pointer in first, but instead deep copied the string data into a new heap allocation. Yep. Okay, shallow, not shadow. Did not shallow copy the pointer in first, but instead deep copied. Okay, so shallow is just a, whatever. I think that's some weird wording, but I guess that's the term. Shallow copying would be... I've not used that term before. Apologies, I come from a land of JavaScript where we don't have to worry about memory. Nobody cares. If it runs like a horse with 2 legs, then get a better computer. Therefore, at L2, the first_clone has been moved and invalidated by adding suffix. The original first variable is unchanged. It is safe to continue using quiz. Which of the following is not a kind of undefined behavior? Having a pointer to freed memory in a stacked frame. I believe that's fine. Freeing the same memory a second time, that is undefined behavior. Using a non-Boolean value as an if condition, undefined behavior. Using a pointer that points to freed memory. No, it's also bad. You shouldn't be doing that. Oh, sorry, missed that. It's but with exclamation because it's more exciting in Rust. I'm sorry, Keith. That was very funny. That was a good joke. Determine whether the program will pass the compiler. If it passes, write out the expected output of the program if it were executed. Function add under suffix mute s type string returning string s plus string world. Right, return s or just s. Do the s. I hate that so much. I'm never gonna stop talking about it. Fuck that. Function main let s equal string from hello. Let s2 equal add suffix s. Right. Line s2. Okay, here's where we find out that I probably wasn't paying attention even though I read the entire thing. Alright, so we're passing s in through add underscore suffix. Then here, we are passing in the value. I don't think this compiles, right? So this would be a copy. This would try and copy, but string doesn't have copy. Meaning it would try and pass a reference. Meaning ownership would pass through. No? I guess I really don't understand this. Let's say it does compile and it puts out hello world. If anybody wants to tell me the answer, I guess I'd love to know the reasoning it wouldn't compile. Right, so here we'd be passing s through a function as a reference, which would be s, which would make ownership the mutable s, and then we would return it. We can't pass ownership like that, can we? Would it pass the value because it's not being copied? Let's see. I guess there's more. Oh no. I really don't think it would compile, actually, now that I think about it. I believe I may have been wrong, because it should be passing by reference there. No, it's not. I don't think it is, because S is immutable. Silver Sorbet, you know more about Rust than me. I guess we'll see. Determine whether the program will pass the compiler. If it passes, write the expected output of the program as if it were executed. Let s equal string from hello, let s2. S2 is, yep, let b equal false. If b doesn't run, print s. Hello. Yes, it does compile, and it just prints hello. B is false, B is a Boolean, that's perfectly fine. This does not run, but it's checked at compile time. That'll never run. I don't think that will compile. Sorry, I think that will compile, but if B was true, it wouldn't, because C is after free. Right, lastly, say we have a function that moves a box like this. Move a box. In a box of a box. Below are 4 snippets, which are rejected by the Rust compiler. Imagine that Rust instead allowed these snippets to compile and run. Select each snippet that would cause undefined behavior, or select none of these snippets if none of these snippets would cause undefined behavior. Let B, alright, so within this, it would take in a B box. Let B equal box, I'll call new, shadowing B. Let B2 equal B. That would not work. What are we supposed to do? Select each snippet that would cause undefined behavior. That's undefined behavior because we are using B after its ownership has been moved. B equals box, colon, new, unless box can be, yep, that's the same thing, is it not? Wait, what? B2. No, it's using B2. I'm sorry about that. It is using B2, and that's fine. This does nothing? Right, that's fine. I believe that's fine. Right, that's not fine because it just uses regular B, not B2. No, that's not fine because of print line. I'm sorry, I'm tired. I'm guessing you guys are ripping out your hair because that was incredibly stupid. Let B equals box, colon, new, 0, move a box B, and then B2 equals B. No, because this moves a box and doesn't return it. Let's say we have a function box that looks like this. Moves a box like this. It moves a box. So it wouldn't, and it doesn't return anything back to B. It's moved the box, so that will fail. Let B equal box, colon, new, 0, move a box, B, print line, B. No, because B is... Now, why I don't like this is that all of these, to me, seem wrong. Let's read through them again, just quickly. B equals box, colon, new, B2 equals B. That should be moved from B to B2. You're trying to print B. That will not work because that's a use after free. Or sorry, use after moved. Let B equals box, colon, new, 0. Let B2 equal B. Okay, so we've moved B to B2. Move a box B. Move after free. Let B equals box, colon, new. Move a box, which moves the box. Let B2 equal B. That's, again, like number 3, a use after move. Let B equals box, colon, new, 0. Move a box B. Print line B. We've moved the box. What's the difference between these two? There's no difference, except we're having new memory. Oh, no, no. Wait, is this okay because it's not actually using it? It's simply it's simply moving a reference to... Because it's okay to have a variable on the stack that is a pointer to memory that has been moved. That's been freed, right? I don't know. Right. Let's see. That's 1 correct. Right, I answered 2 of 4 correct. Which of the following is not undefined behavior? That's correct. This does compile, and it is hello world. Okay, I guess I was wrong with that. So it isn't because it is immutable. It's mutable within this, so that's a copy. That is copied, man. It has to be copied. It has to be copied. That has to be passing by value, not by reference, then. So this has to be passing by copy. By copying. This can't be a pointer being passed here. Because S... Right, fine. I'm sorry for this. Is anybody else just very confused by this? Yeah, we're both confused. We're all 3 of us are confused here. Right, so we have... Let's play around with this. So we have... Can we try using S? Just S. No. Because it's been moved. Why is it... Did that state why it's been moved? Right. Unused variable. Borrow a mood value S. Move occurs because S is of type string, which does not implement the copy trait. Value is moved here. It's moved here. So is moved as is being passed to add underscore suffix to s within here, which is mutable. Which is mutable. Okay? Why is... So it's immutable. It is not mutatable here. Not mutable. But it is mutable here because the pointer's been moved. Why can't we change... Right, so it's... Okay, I think I do understand, though I don't fully understand why we can change it from an immutable to a mutable variable. I guess that's just the compiler time checking. From this point forward, you can mutate it. We have stated as much. Mutable isn't something that's actually part of the underlying technology, just something that's checked for at compile time, which I mean makes sense. That's what a lot of this is for. This is just changing a lot of runtime checking to compile time checking. I think I do understand this now. So the movement of this would be S starts on the stack of main, in the frame main. The stack then goes... Do you guys want me to try and explain it in color paint? Stop me if you just want to continue. Is this a thing? Do I not have color paint? Yes? I guess I need to get color paint. Thank you. That's fantastic. I thought I had color paint. This will take just a moment. I should have had color paint here first, but I didn't because I'm an idiot. Yep. Right. So that's useless. That is incredibly useless. Hey. Alright, so you have main inside of a frame. We have let s, which will make s equal to... How did they... How did they list it off here? Right, yeah, I guess they just had it in a box. S equal to HELLO, some string, some words. At which point, we have S2, which is... This is location 1. L1. This will be location 2. We have main, which has a box for S. Okay, yeah. Location 2 would be... Let's have location 2 be here. So, from location 2 here, we have... Right, so from main we have S, which has the string hello inside of it, originally inside of its frame here. Here we have F, we have main, where S equals a string. Well, no longer actually. This is no longer there. It is moved inside of add suffix. This is so trash. This is so trash. I am sorry. This is a disappointment. My father is looking down upon me with anger, and he's not even dead. Why is Color Paint doing this? Green open source software, my boy. Ah, wow, that's wonderful. Don't we love this? Don't we love this community? Oh yeah, sort of it. And then we have this, which also has S. Oh, that's great. Sure. Some text. This is very helpful, guys, right? Can you not understand everything I'm doing here? And I hate color pink. What the fuck is this doing? Right, fine, we're going Krita. Discard. Going to Krita. Didn't want to show you my art because it's trash, but we're going to Krita. We're going to Krita. Love Krita. Apologies for the weeb shit. Hate how this is the image. I wish they just had like a scenery. Anyway, new image. Create. Here we go. So we have main. Where are you guys? Pinta. I do not have Pinta. We have main. A shrimp from a video game. What video game is that? What video games have shrimps in it? I love shrimps. Splatoon. Ah. Aren't they squids? I thought they were squids. Or maybe they were kids. Do they legit have shrimp? Is there like a race war going on in Splatoon? Oh, well, that's very helpful. I've gotten to the end of my canvas, haven't I? Right, so originally we have S, which is some string value. Secondarily, we have S, which is still some string... Sorry, we have S... Huh, no, okay, so thankfully I did this. Right, so now I'm just droning on and wasting everybody here's time. Originally, we have inside of main a frame with S in it, which is a pointer. Sorry, we have S, which is a pointer. We'll put that as a pointer to heap data with a string in it. Secondarily, we have main. There are other marine animals in there. Like what marine animals? S, which is a pointer to random memory. I swear I'm better at art than this. As well as within add, this is very helpful, guys, is it not? It has S, which is a pointer to the original string, and thank you, to the original string inside. I don't think this is helpful. I'm a failure, but I'm okay with that. Thank you guys for not judging me too hard, or judging me incredibly hard, but leaving that in your own home. Anyway, so originally we have S, which is a string from hello, and when we try and pass that into add suffix, a new variable called S is created, which takes the original value of S, which is simply a pointer, pointing to this string, just a label to a cubby hole with a whiteboard with the word hello. Or sorry, yeah, hello. Right? It just takes that label, puts it onto S, and this is just pointing to some random memory. Secondarily, when we pass it back, we are just passing back a value at S2, I believe. No, because you can't pass back the value. Once more, we are putting it back at the third place. In main, we have S again, which is once more, sorry, S2, which is once more a pointer to this word, but we have pushed a string world in. Oh, sorry, yeah, I guess it would really be useful to draw that piece because something interesting happens there. So at this point, I think that I at least understand this. I apologize if you guys don't. At this point, however, S is in memory. It exists. Have S. with a pointer to world, but we need to destroy S. We need to take this memory, which only is 1, 2, 3, 4, 5, 6 bytes long. We need to destroy this. Well, that's not actually destroyed. That'll be there forever. We need to destroy this. Create a new piece of memory. Sorry, we need to create a new piece of memory, which is larger, that we can add in world, actually. Right, okay. I think we're getting here, but I'm bad at this. So originally we have S, which is pushed into here by reference, meaning that this is now to random memory. Sorry, this is now to this. Originally we have S, which is a string hello world, a pointer to string hello world. When we pass it in here from add suffix, into the function add suffix, we are moving it. S no longer owns this. This is gone. This no longer owns S. S is now owned here within this variable. We then push in the string underscore world, which will destroy the original bit of memory here in the heap. Hello will destroy, no, it won't. It won't destroy it for now. It will create a new section of memory that can fit in hello world. It will add in hello world to this bit of memory, and then it will destroy the original piece of memory which we created from this string. Thank you, Silver. I'm guessing that you were reading from here instead of my inane rambling. Thank you for standing by me. Unless you're just saying that to get me to shut up, which is fair, honestly. At which point we return it by reference again. So S is no longer owned here. S is owned by S2. The ownership transfers every time we return. Every time we make a new variable, use it. Ownership is here, meaning it will fail here because, well, of course, ownership is on S2. So to confirm, passing something to a function will pass ownership as well. Unless we use something like dot clone, right? That should, that won't work at all because that's not a thing. S2 is unused, at which point S is fine. Yep, because we're passing by value instead of reference. Apologies for the value versus reference piece. Again, JavaScript, that's the entire thing. I think I got a text. I did not. Okay. How about you, Keith? How are you on all of this? I can understand a bit of confusion. I was very confused myself. I'm going to wait a moment for your response. I believe there is still a bit of a delay here. I do apologize for that delay. I wish I could fix it, but I cannot. I think it's a bit worse today. Yeah, I can fully understand this. This is a bit of a thing to wrap your head around. Ownership seems quite difficult. Yeah, this is one of the more theory-heavy parts. I completely agree. I can usually teach memory to somebody. Of course, one-on-one is very difficult for me with the entire being recorded thing. But ownership is something I'm going to have to figure out how to explain to people. It seems that they think that you already understand how memory works for some reason. Like, they keep using the heap and stack as if you know what these things are. As if you know that a string is simply an array. An array is simply a pointer to the first value in is proof by intimidation. Common in physics books. Okay, that's very funny. I am sorry for all of you physicists. But like, they make you think. They don't explain any of this, which should really be explained, or at least you should be told that you need to know this stuff. When I was learning C, the book specifically stated you need to know these things at this point in time. Crafting Interpreters by Robert Nystrom, great book by the way, just told you outright, you don't know the stuff, go learn it, come back in a month. Just great book. But like they seem to think you're going to understand this stuff before actually, when you're on the, hey, let's learn the basics thing. But in the previous things, they just didn't. I don't know, maybe they're going to just explain how memory works at some point, or maybe they don't think you need to know. Right, so let's just continue after that massive, droning sidebar. Variables live in frames. A frame is a mapping from variables to values within a single scope, such as that's thank you, you've done all this. Right, so this program, okay, yep, this was correct. Here is where we were, right back there, like half an hour ago. Determine, yep, so this program does compile. Hello. Right, yeah, I guess so. Why does this compile? Yeah, it should compile. Why did I not say it compiles? Of course it compiles, because again, I think I explicitly stated B does not run, because this is false, this will always compile. I don't know why I said it didn't compile. Alright, this one I believe I am incorrect. On normally. Right, okay, so I had said all of them are incorrect. Which one is correct? So which one does in fact work? It doesn't say it. The key idea is when a box is passed to move a box, its memory is deallocated after move a box ends. Therefore, reading B via print line after move a box is undefined behavior. Correct. As it reads freed memory. Giving B a second owner is undefined behavior, as it would cause Rust to free the box a second time on behalf of B2. It doesn't matter whether the let B2 equals B binding happens before or after move a box. However, doing let B2 equals B and then print line is not undefined behavior. Although B is moved, its data is not deallocated until move a box is called at the end. Therefore, the program is technically safe, although still rejected in Rust. Oh, okay. Okay. The thing which is safe here is, that's unsafe. So this is unsafe. That's safe? Why is that safe? Yeah, because it's not deallocated. Okay, so I was thinking, would Rust compile this? Not, is this safe? I guess I didn't read it correctly. I understand. This is safe. This is completely safe because B is never deallocated. Or sorry, isn't deallocated until the end of scope, which does not happen within this space. But in Rust, the ownership has moved. B2 now owns the box new 0 instead of B. So any usage of B is a failure within Rust. It will not compile. However, this is safe code because B is not deallocated. Okay, makes sense. I can understand why that is safe code, but is still not allowed in Rust. Summary. Ownership is primarily a discipline of heap management. All data must be owned by exactly one variable. Rust deallocates heap. Oh, okay, so we can't have two variables that have any ownership. I was thinking, like, could we have two pointers to the same heap memory? But no, I guess we cannot. Well, we can, but we can't use two pointers to the same heap memory due to the fact that it is not owned by both variables. It's only owned by one. Rust deallocates heap data once its owner goes out of scope. once its owner goes out of scope. Understand ownership can be transferred by moves, which happens on assignment function calls. Okay, it perhaps did explicitly state that thing which gave me a bit of a difficulty there, but I guess I glossed over it. Heap data can only be accessed through its owner, current owner, not a previous owner. We have emphasized not just we have emphasized not just how Rust's safeguards work, but why they avoid undefined behavior. When you get an error message from the Rust compiler, easy to get frustrated. You don't understand why Rust is complaining. These conceptual foundations should help you with interpreting Rust's error message. It should also help you design more rustic APIs. 1? Where's 1? I don't care about footnotes. I've never read them before. I'm not going to read them. I don't care. References and borrowing. Ownership, boxes, and moves provide a foundation for safely programming with the heap. However, move-only APIs can be inconvenient to use. For example, say you want to read some strings twice. M1 equals string from hello, M2 equals string from world. Greet M1 colon M2. S equals format M1 M2. Error. M1 and M2 are moved. Okay, holy shit. This is going to cause an absurd amount of errors because there's no explicit. Yeah, I can understand why this is going to be so bad for me. Because you call something with these into it, and I'm thinking it's passing by value because JavaScript. I'm a script kiddie. I'm a child who has been playing in a world of garbage collection and type, and just random typing without any real causes. I'm just a kid in a sandbox. But now I'm here in real world, and this is something I have to worry about. Any call, yeah, I can understand. References, borrowing. Oh, that's what borrowing means. We're not. I don't know, man. I think I understand what borrowing means now. That's really cool. That's a great name. Right, so let's go through this. We have L1. Location 1 is within greet. So we go through this. M1 is a thing called hello. M1 is a thing called world. Greet. Classes M1 and M2. M1 and M2 don't exist yet. Well, they exist, but M1 and M2 pass ownership. They no longer own the values. It goes into greet. At L1, we no longer own it here and here. Greet owns 1 and 2. Sorry, I'm just pounding this into my head, ensuring that I know it forever. And I'm going to forget it instantly. L2, after we've printed these things, we go to L2, which is back here. Okay, after it has returned, returning nothing, we have this. G1 and G2, now out of scope, are collected, garbage collected. I mean, come on, they're garbage collected. That's really what's happening here. This is just a weird pseudo garbage collector. Unless I fully misunderstand what garbage collection is, I guess I probably do. But they are deleted. They are yeeted from memory. They are no longer there. Or, well, they're still technically there, but our program has said that they're not being used, and thus they can be allocated by another program. The operating system will take care of that. M1, M2 do not own anything. And when we try and access M1, we cause an error. Undefined behavior. An example calling greet moves. In this example, calling greet moves the data from M1 and M2 into the parameters of greet. Both strings are dropped at the end of greet, and therefore cannot be used within main. If we try to read them like in the operation format, which is a macro, then we would be that would be undefined behavior. The Rust compiler therefore rejects this program with the same error we saw in the last section. Borrow of moved 1. Rest of the error. Error. The move behavior is extremely inconvenient. Programs often need to use a string more than once. An alternative greet could return ownership of or returning it. Okay. I thought there would be like some right, so my guess was that we would put some okay. My guess was that we would put something here, like M1 colon borrow, M2 colon borrow, and then it would be passed back here. But no, we have to pass it back to a new variable. We have to pass the reference back into it. Okay, I think I can understand that. If we pass the reference back in, then it's re-owned by M1 colon again and M2 colon again. Not colon, underscore. Right. Secondarily, we could just have this be M1 and M2, and it will shadow the original. So, I don't think that would be an issue. That cannot be bad Rust. I think that's really what this is trying to push us towards. I think soon it's going to tell us you can just shadow these things. And here we have it returning two variables inside of a tuple. No, not a tuple. What am I talking about? It's just returning two values. That's quite Go-like that. However, the style of program is called. However, this style of program is quite verbose. There's some wordings here that I just hate. A non-English speaker would have a hell of a time here. Rust provides a concise style of reading and writing without moves through reference. Yeah, that's... yeah, that's not... Okay, unless there's some really weird stuff going on here and they've decided to completely change this. This is just passing by value. This isn't rewriting in a more convenient manner. This is passing by value. Right, unless it's... Okay, so we have M1 string colon hello. M2 equals string colon world. Then we have greet, passing by value M1 and M2. Note the ampersands. Print line, the values hello and world with a space in between. Then we have then we have format, let s equals format, hello and world, which utilizes M1 and M2, which never passed ownership over to G1 and G2 in greet. Now, this isn't the same as this. This is not the same as this, because this is passing the pointer. And we'll see. Is this not a redirection? Is ampersand a redirection in C? I believe somebody here uses C a lot more than me. It's been like quite a while. Ampersand should be... Is ampersand the pointer? Is ampersand a pointer? Right. Redirection operator in C. Not a worry, Keith. We just went through something very strange. That's not what I wanted. We are not working on a question. We are continuing to read references and borrowing, which so far we understand very little. I'd have to go through the entire thing to get back to this point. Apologies. Right now I'm trying to figure out what's going on. Okay, so ampersand is reference, and my confusion was wrong. So a star would in fact be in C regularly value instead of reference. Okay, I guess my... Okay. Then that's a lot better. Apologies for the frustration here. I was very wrong. Thank you, Silver Sorbet. I'll fully understand that I was wrong in that section. Right. The expression ampersand M1 uses the ampersand operator to create a reference to, or borrow, M1. It passes the pointer. The type of the greet parameter, G1, is changed to pointer string, meaning a reference to a string. Oh, okay, so it isn't switching them. I was just completely incorrect. Alright. Egg on my face. Apologies for that, everybody. So ampersand is just pointer. That's reference. That's not redirection. That is pointer. Okay. The type of, pointer string to be a reference to a string. So ampersand string is reference string. I'm going to have to start using reference string because it doesn't seem like there's very much of an idea of pointers in Rust in the same manner as C. Which is okay. Observe that L2 there are two steps from G1 to the string hello. G1 is a reference that points to M1 on the stack, and M1 is a string containing a box that points to hello on the heap. While M1 owns the heap data hello, G1 does not own either M1 or hello. Therefore, after greet ends and the program reaches L3, no heap data has been deallocated. Only the stack frame. Okay. Alright, so G1 is a pointer. Oh! Okay! Okay. So G1 is a pointer to M1, which is a pointer to hello. Okay. So it's just a pointer. It's just a pointer. And if we were to pass it through, again, it would be a pointer. A pointer to a pointer to a value. Okay, that makes a lot of sense. Well, M1 owns the heap data hello, G1 does not. Yep, so that's a pointer. References are non-owning pointers because they do not own the data that they point to. Do they? I think that this is just a little bit of fuddling around on Rust's part. I think they understand that G1 does technically own its value, which is not hello. It is a pointer to M1. And it's just redirecting it all the way for you. It's dereferencing. Twice. Okay? References are non-owning pointers because they do not own the data that they point to. I disagree. The previous examples using boxes and strings have not shown how Rust follows a pointer to its data. For example, the println macro has mysteriously worked for us for both own strings of type string and for string references of type string. They're a reference string or pointer string. The underlying mechanism is the dereference operator. Yeah, that little confusion at the beginning is quite embarrassing because I was basing my confusion off of the understanding that the ampersand was a dereference operator. That's a bit of idiocy. I'm just going to state it again. I am a moron who writes mostly JavaScript, so that's my excuse. I'm a JavaScript boy. That is my excuse. Excuse my idiocy. I'm a web programmer. For example, here's a program that uses dereferences in a few different ways. Let mute x box I32. I am very happy. Right, let mute x box I32 box new 1. Let a I32 equal reference, dereferenced x. Dereferenced x reads the heap value, so a equals 1. Are you lost, Keith? Because you did miss quite a lot. How much did you miss? Dereference x equals plus equals 1. Okay, so x reads the heap value, so a equals 1. Yep, so that's just passing by value. Dereference x is 1 plus equals 1. Sorry, Keith. Well, VOD's still up on YouTube if you want to check it out later, or you can read this yourself, if you're going to do that anyway. This is going to fail, isn't it? Dereference x on the left side modifier modifies the heat value. Okay. That's weird. I don't understand that at all. To me, that reads like 1 plus equals 1, which should fail. But instead, that's... Would x plus equals 1 make it the next pointer? That would be an error. Let's copy this stuff and paste it here. Apologies for this. Oh, that's... so that just took an entire function based off of that. Right. What in the world did that do? That is apparently formatting. Thank you for that. Right, would this cause an error? No. Can we print x? I'm never going to remember how to do a print line in this language. That's not going to work. All right. Cannot use on box. Okay, I understand. Okay. I do understand. So this is x is of type box I32. X is not 1. Oh my god, I'm an idiot because that's explicitly stated right here. It's literally telling me that yes, x is of type box. Yep. Also, that should be a bit bigger. We learned that last session. Okay, I do understand now why this is there. Fine. The reason that for anybody who's watching the VOD, because I understand Keith and Silver are maniacs, they are gods, they are beautiful men, they fully understand this. Dereference X is dereferencing. Okay. So box, the function or method, new off of box, creates a pointer. I don't know how to explain this properly. I think I understand it, but explaining it's another thing. Box will create, through this function, a variable with the value of 1. Sorry, we'll create heap memory with a value of 1, and a pointer to said value. However, that is not what is returned. We are probably returning some form of struct with that value and some other information back as a type box I32 to X. And when we dereference, we are dereferencing down to that pointer that we can change. Because in C, I'm fairly certain that dereference X would be 1, not the variable holding. So trying to change that would be like 1 plus equals 1. Perhaps I'm wrong on that, honestly, and this has been useless rambling once more. Observe the difference between R1 pointing to X on the stack and R2 pointing to the heap value 2. R1? Yep, R1. Alright, so X is pointing to 2. A? Oh, sorry, we were not done. Let R1, which is a pointer box I32, our reference to a box of I32 equals a reference to X. R1 points to X on the stack. Okay. Let B of type I32 equal dereference R1. Dereference twice R1. The first two dereferences get us to the heat value. Okay. So I guess my initial understanding was wrong. So first dereference, R1 turns into X, which is of a box I32, which is box : new 1. Dereference secondary brings us to the value 1 within the heap. Okay. So there's no alternative variable being created by box. I was wrong with that. Okay. I guess that's okay. I guess all the magic actually is just happening at compile time. Not a worry. And then B equal, yep, 2 dereferences gets us to the heap value. So first dereferences gets us from R1, dereferenced, gets us to X, dereferenced again, gets us to the value of 1 as seen here. Let R2 of type reference to an I32 equal dereference to a dereferenced X. Y'all understand that? Y'all having a good time? We are looking for a reference to the dereferenced X, which is borrowing the heat value. Sorry, no, it is getting a pointer to the heat value, referencing it directly. I guess that is borrowing? We'll learn soon. C of type I32 equal the dereference of R2. So only one dereference is needed. Right, R2 points directly to the heat value. Sorry, yeah, I was thinking this. What was that? R2 points to the heat value directly. Reference 2 points to the heat value directly. So only one dereference is needed to read it. So this, R2, doesn't equal X. It equals the heap memory that X is pointing to. Sorry, no, it equals to a new reference to the heap value that X is pointing to. Yes. Yep, so we have this wonderful graph here, which shows us that we can have two pointers to the same amount of heap memory if we do it in this very weird way. Meaning if we were to change R2 here, R2 and X would change value. Let's see. Wait, what's wrong with this? What was wrong with this? Yep. Let's just copy this over, because I'm just gonna check this over. See if I am correct in this. If we try and print Y, is it capitalized? I have no idea why it is not letting me have the snippet for print line. That should work, right? Am I incorrect in how print line works, or am I going to have to create new snippets? I have no idea. Or is my shit still fucked? Alright, we are trying to output X. Let's mute. Alright, so now we want R2 plus equals. Now we want reference to R2 plus equals 1. Is that fine? So if X equals 2, we should be outputting at this point 3. What's wrong? Not assigned to as, which is behind a reference. R2 is a reference, so the data it refers to cannot be written. Consider changing this to be a mutable reference. Okay. That's 10. Did I forget to save? What's wrong with this? That's now a mutable reference. That's now a mutable reference. What? What is it trying to get me to do? That's what you told me to do. That what it's trying to get me to do? R2 is a reference, so the data it refers to cannot be written. Help. Consider changing this binding's type. Oh, okay. Yeah, because the type needs to be mutable, of course. You should understand that. Yep. Let's try this again. Oops. It's fine. Okay! Okay, there we go. So yes, we can have two references to the same value. What if this is immutable? Oh no. Ah! Ah! Okay. Okay, that's good. Apologies, this was just me playing around a bit. What I've learned so far is pretty cool. So we can have, in fact, two pointers, two references to the same heat value. And later on, we can change it only if it is originally mutable. So we can't have a situation where we later on create a mutable reference to a immutable object and then mess with it, which is very good. But if we have two references to the same data and it is explicitly mutable in all places that it is referenced, or sorry, in both the place that it is referenced at as a mutable reference and separately mutable originally, it'll work. That is really good. That is really good. I really like that. Yippee! Hell yeah. I hope somebody else but me learned anything from that. I really doubt I explained things very well as I was doing them. But that is really quite good. That's a lot of information that I really like to see. And they're probably going to explain it later on here, but I'm an idiot who learns by doing. You probably won't see it's not idiocy to learn by doing, to be entirely clear. I'm just an idiot who separately learns by doing, to clarify. You probably won't see the dereference operator very often when you read Rust code. Rust implicitly inserts dereferences and references in certain cases, such as calling a method with the dot operator. For example, this program shows two equivalent ways of calling i32 : abs, absolute value, and string : length, string length function. Let x box i32 equal box new -1. Actually, if you learn by doing, you might be interested in rustlings. Rustlings. I was thinking of doing Advent of Code, but if there's a thing called rustlings that does like small that is really cool. Small exercise to get you used to reading and writing Rust code. Favorite. That's in my favorites bar. Thanks, man. Greetings and welcome to Rust. Let's read this together just a little bit. Greetings and welcome to Rustling. This project contains a small exercises to get you used to reading and writing Rust code. This includes reading and responding to compiler messages. Look for the old, web-based versions of Rustlings. Try here. Alternatively, for first-time Rust learner, there are several other resources. Rust the book, which we are learning, and Rust by example. And Rust by solving little exercises. I see. I think I prefer Rustlings because it's made by some random dude. No, it's not. It's made by Rustling. What's the difference? Thank you, Silver. I'm going to mess around with this. I'm going to post this into the main thing, and perhaps on Thursday. I missed last Thursday due to family stuff. Well, I haven't been too active, but I will be absolutely learning with this. This is fantastic. Seriously, I can't thank you enough, man. Right. Probably won't see it very often. We have box, let x equals box I32, box new, -1, let x abs 1 equal I32, colon, app. Implicit dereference. Is it implicit? Where's the implicit? Oh, explicit versus implicit. I see. Ah, okay, so using a dot method on x, which is just a method on type I32. I see. That will implicitly dereference the value, which is what you'd want. I can see. Alright. I wonder why this would be something you'd want to do. I guess more explicit, being more explicit. Let R, reference to box of type reference to box I32 equal reference X. Let R, absolute 1 equal I32, colon, double dereference R. Oh, okay, so it will fully dereference it. It will fully dereference it to its value, because why would you want the absolute value of a pointer? That would be dumb. Assert equal, it will be true, of course. Let S equal string, colon, from, below. Let S underscore line 1 equal string. Yep, I think we understand by now. That's good. I'm always going to use this and never this, as apparently it's trying to push me towards I'm an idiot and hate all of this. What the fuck is all of... Where is it? It's no longer here. I hate all of this. This stuff. This stuff makes me sad. What in the world is that? Right. Where were we? I missed us. I messed us up. I'm a failure. Here we go. This example shows explicit conversions in three-way. I don't think we really need to read this too much, but I'll just skim over it. The I30, yeah, yep. Right, I think we can understand what happened here. This one does it twice. I just read it myself without reading it out loud, which is stupid because, yeah, I don't know it. Consider the following program showing the state of memory after the last line. You know what? Actually, no. Let's just read all of this. Apologies. That is what this is for. The I32 colon abs function expects an output of type I32. To call abs with a box I32, you can explicitly dereference the box like I32 colon abs, dereferencing X. You can also implicitly dereference the box using method call syntax like x.abs. Syntax. Not a worry. Thank you for being here, Keith. Hope that you can read the rest of this on your own. Have a great day. The dot syntax is syntactical trigger for function call syntax. The implicit conversion works for multiple layers of pointer. For example, calling abs on a reference to a box R colon reference to a box I32 will insert two dereferences. This conversion also works the opposite direction. The function string colon length expects a reference of string. If you call length from an owned string, then Rust will insert a single borrowed operator. In fact, there is a further conversion from string to str. Oh, okay. We will say more about method calls and implicit conversions in later chapters. For now, the important takeaway is that these conversions are happening with method calls and some macros like println. We want to unravel all the magic of Rust so you can have a more clear mental so you can have a clear mental model how Rust works. Let's start this. Consider the following program showing the state of memory after the last line. we have box x equals new this, but let y equal box colon new, which is a reference to x. This is not something we've seen. Okay. If you wanted to copy the number 0 through y, how many dereferences would you need to use? Write your answer as a digit. For example, yep. Right. So if we wanted to get that, that would be dereference x. So if we wanted to get 0, we would have to be dereference x to get that there. So now we have new box. Okay. So we have, it will originally be that, get the value, x, get the heap memory x. In order to change it, we will need to be doing this instead of that. Now, y is equal to the reference of x. Y is a new box, which is equal to the reference of x. So if we need to dereference it originally, we need to dereference. Right. So dereference y would equal a pointer to x. Would it not? Yes, because the value of y is a new box of type x. If I want to get to x, I need to dereference y. Okay. So in order to get to simply x, we need to dereference y. So, if you wanted to correctly put out 23, I would need to dereference it again. So that would equal that. Double dereferencing y would be equal to dereferencing x once, due to the fact dereferencing y would equal x. This is the theory. This is the idea. If dereferencing x equals the heap memory 23, then if we were to make y equal box new type x, a reference to x, dereferencing y equal the reference to x, as is the value inside of box colon new. Later on, in order to get the value, we need to dereference it twice, because we would need to dereference x to get 23. As this is a reference to x, and to get 23 out of x, we would need to dereference it. So dereference y. I believe the answer is 2. I could be wrong and it could be 3. Consider the following program, showing the state of memory after the last line. Function, get underscore first. VR, colon, reference to a vector of I32, pointing to returning I32. And we are returning. I hate implicit returns. I hate them with a passion. Again, not going to stop talking about it ever. Function main, which runs let mut v equals new vector is 0, 1, and 2. Let n equal get underscore first, a reference to vector. Passing it in, we are expecting a reference. Fantastic. And we are simply returning the first value, which is 0. Right. N equals what I would assume to be value 0, because this is a vector, and we are returning the value, as this is also a macro. This should be a macro. In C, this is a macro. We haven't discussed this, though. Which of the following best explains why V is not deallocated after calling get first? Okay, so that's all it's asking about. Why are you complicating it? Well, I guess I can read the entire thing. Right, so which of the following best explains why v is not deallocated after get underscore first, because it's passed via reference. Get first returns a value of type i32, not the vector itself, incorrect. vr, well, that is correct, but that is not why it is not deallocated. vr is not mutated. That is not the reason. V is used after calling get underscore first in the print line. That's irrelevant. vr is a reference, which does not own the vector it points to. I forgot about that. Yeah, the real reason is because vr is a reference that does not own it. I can understand that. Great stuff. It's 3, isn't it? Let's just see the correct answer. It's 3! Okay. Okay, I can see why now. I can see why it is, in fact, 3. To confirm, this is equal to that. I can see why now. This is a reference to x, which we must dereference in order to get x. So, dereference of reference x is equal to x. Okay, so I guess the updated version of that explanation would be, if we have x equals box new 32. Well, that's actually not, this isn't code, but whatever. We have x is equal to box colon new 32. The reference of x equals 23. Apologies. 23. If x equals a new box of 32, dereferencing x gets 23. X is a reference to the memory, sorry, the heap memory of 23. Y, right, so we need to dereference it in order to get to 23. Y is equal to the reference of x. Sorry, the dereference of y, which here is a new box of type reference x, equals, right, so dereferencing y will get us the reference to x, which must be dereferenced in order to get x, which once more must be referenced to get us 23. So this is the path, I guess. X equals box colon new 23, dereferencing x equals 23. I'm just going to get this all listed out. X equals box colon new 23, dereferencing x gets us 23. Y equals box new reference to x, dereferencing y gets us a reference to x. In and of itself must be dereferenced to get x, which must once more be dereferenced to get 23. This means that there must be 3 dereferences before we get 23. That was a long, droning on, stumbling way of explaining things, but I personally understand. I don't know if you're still here, Silver, but do you understand what's going on? I would understand if you need to leave. It's been 2 hours, and that is usually the end. We're not even halfway through. I don't think we're going to get through today. I think I'm going to get to the end of this and finish this off. Apologies for that. If that's okay with you, Silver. You're still here? Good to hear. I'm glad that you understand it. I believe I do now, too. Confirm, are you cool with ending, getting to the end of this and then just stopping? Sorry, you said yeah, but I don't really know at what point you said that. I guess I should put long pauses between. I'm going to continue reading until you state so. Rust avoids simultaneous aliasing. You're ready to stop now? Alright. Well, I'll see you later. I am going to, for the VOD, simply... Actually, no. It has been 2 hours. This is going to be part 1. Thank you so much, Silver Sorbet, for joining us here. I'm going to stop at this point and explain so on Lemmy. I wish to see you next time. I'm probably on Thursday going to go through your suggestion of rustlings. No pressure to be there if you don't want to be. Once more, I guess I'm just going to repeat myself. Thank you for being here. I guess this is the end. See you later, Sorbet. Have a great day.